Right, let's jump straight into it. Welcome to The Explainer. Today, we are setting out on a genuinely wild, multidisciplinary ride. We're going to unpack this incredibly dense, almost poetic collision between 400-year-old philosophical concepts and hardcore modern software engineering. We're looking at exactly how abstract blueprints actually become living digital realities and how that translates to the absolute cutting edge of artificial intelligence. It's a deep dive for sure, but stick with me. We're going to build this step by step so it all makes sense.
So, here is our cognitive roadmap for today. We'll start with 1. The blueprint and the moment. Then 2. Code and runtime trees. 3. The event-driven database. 4. Reconciling philosophy and mechanics. 5. Multi-generational swarm commits. And finally, 6. The bit-perfect future.
Section 1. The blueprint and the moment.
Okay, let's dive into this. I want you to listen to this quote straight from Volume 0 of the Journal of Hegeliae Universale. It reads, "A pre-runtime JavaScript file is Hegeliae Universale, and a runtime instance of that file is Hegeliae." It's such an amazing statement, right? Because it instantly bridges the profoundly abstract with the highly technical. It literally takes ancient scholastic philosophy and applies it directly to how a computer parses a file.
Let's make sure we define those terms clearly so we have them locked in. Universality. Well, think of that as the eternal, static blueprint. It's the pre-runtime instructions just sitting lifeless in a text file. It is the abstract potential of a thing. Hegeliae, on the other hand, essentially translates to thisness. It is the unique, ephemeral existence of a thing in a highly specific moment. It's the live runtime instance happening right now in the computer's memory. This philosophy is basically what gives life to a static instruction, allowing it to exist uniquely within a fleeting duration of time.
Section 2. Code and runtime trees.
Now, what's really interesting about this is how it maps to the real-world experience of a developer. Think of the code tree as the static algebraic blueprint. Contrast that with the runtime tree, which is the dynamic, live environment. We can actually trace this directly to a June 19, 2020 mid-tax email from Kyle Smith. He explicitly outlines how code and runtime trees must perfectly reflect each other. This is a core concept that anchors what the research refers to as pillars 4 and 5. Every single time a programmer runs a script, they have to seamlessly jump back and forth between these two expressions, quite literally witnessing philosophy in action without even realizing it.
Section 3. The event-driven database.
So, how does the system physically support this dynamic jump? Well, it requires specific engineering, which is outlined in the SeedTreeDB patent. It operates through an entirely event-driven paradigm. Step 1. A static parent vertex receives an event, like a user clicking the button or a new piece of data coming in. Step 2, completely responsive to that live event, the system instantiates a brand new child vertex to hold the data. And Step 3, a kernel function physically links them together. It dynamically spawns live data nodes directly from static parent scripts.
And because of this step-by-step kernel linking, the database doesn't just sit there. As the text notes, this tree database grows without bound, literally limited only by the available hardware resources. It unfurls continuously, physically manifesting the passage of time and accumulating real-world live events into a structured, searchable reality.
Section 4. Reconciling philosophy and mechanics.
And this brilliantly illustrates that connection. Think of the algebraic code as an acorn, a compressed, perfectly static blueprint. But what comes next? The slow, recursive unfurling. The acorn becomes the sprout. The static code gives birth to a branching structure of instanced meanings within the runtime tree database.
So the crucial point is that a live computational environment, like SeedTreeDB, physically bridges these two worlds. It mechanistically reconciles the eternal blueprint, the universalia, with the unique, fleeting moment, the hagiatate. Every kernel trigger is an act of philosophical reconciliation, perfectly cementing pillars 4 and 5 right into the architecture.
Section 5. Multi-generational swarm commits.
Let's elevate the stakes here and bring in the multi-generational metagit swarm. When AI agents collaborate, they can easily fall into what's called confabulation consensus, which is basically a recursive loop where they all just agree on a shared hallucination. To stop this, they operate strictly behind a semantic firewall. They use virtual sharding, which means running operations through discrete GNU screen windows, completely isolating their tasks so context doesn't leak. And most importantly, they execute reasoning tree audits through mandatory halts. They intentionally inject cognitive friction to hit the brakes on runaway AI logic.
When we slam the technical execution of a metagit command line interface right into the abstract mathematics of probability fields, how do we actually bridge the gap? We do it through commit strikes. Just like our event-driven database locks in a live node, multi-generational AI agents use these hyper-precise commit strikes to lock their reasoning into bit-perfect physical realities on the file system.
This entire protocol is all about neutralizing stochastic drift. You know, that tendency for AI to just wander off into approximate nonsense. By forcing an audit of each reasoning branch through cognitive friction, the system demands that consensus is a product of physical state evidence on a true forensic floor, rather than just subjective agreement between bots. The AI isn't just generating text, it's mechanistically reconciling its thoughts into a fixed, highly auditable runtime tree.
Section 6. The bit-perfect future.
Let's move to the ultimate conclusion here, which leaves us looking at two fundamentally different futures for computation. Legacy systems rely heavily on continuous polar manifolds, spaces of probability where stochastic drift and AI hallucinations are frankly inevitable. But this research advocates for the rational lattice, a system of pure integer geometric rigor. It bypasses guessing entirely, ensuring every single piece of data is forensically unique and perfectly auditable.
Which leaves us with a massive, and I mean massive, question to ponder. As we demand more complex, infinite context AI orchestration in our daily lives, how will we build true stability? Will the future of AI remain tethered to continuous, drifting approximations, or will we demand the bit-perfect forensic rigor of the rational lattice, forever anchoring the fleeting moment to the eternal blueprint? It's a profound engineering challenge, and the answer will absolutely define the next era of technology. Thanks for joining me on this explainer. I really hope this helped map out these incredible concepts for you. Keep learning, and I'll catch you on the next one.